try to stick to the script a little bit better. I usually just like talking about this stuff and bounce from topic to topic, but just to try to keep it straightened out with respect to your textbook and everything else. So we can kind of derive formulas for these things, but it's one of those ideas where you can kind of get it from the concepts already. So let's revisit the idea of space curves and then derivatives as velocity vectors, and velocity vectors as really tangent vectors, and then we can find tangent lines. So I kind of want to nail down the first three here in, well, the tangent unit vector, we'll talk about that in a little bit. But I just want to nail down this idea from the example, the last example that we did, just so it's not all disconnected. So let's start with a vector valued function, and I'm hoping that you're comfortable with the idea of vector valued function already. And we'll use the same vector valued function that we saw last time, the helix. And so from here, we could take the derivative of any vector valued function, and the derivative of this particular one is just a component-wise derivative of the original vector valued function. Probably should have done that in a different color. So just as a clearer explanation, it's a component-wise derivative. Each component is a function. Even if you see a constant there, you can treat it like a function, so a derivative of that would be 0. But each component is a function, and so if we want the derivative of a whole vector valued function, then we just go component by component taking derivatives. So that doesn't seem to be a big deal. It seems to be kind of natural to do. And then this idea of finding a unit tangent vector is also going to come into play as something that's going to be important for us. And I have a vector here. I can find the vector at a specific point by plugging in a value of t, but I can also find what's called a unit tangent vector. In general, without putting in a specific value of t. So remember that idea of finding the derivative back in Calc 1? You find the derivative, but that's not your slope. That's the slope function. If you want a slope at a particular point, you have to plug in the x value. So the same thing for here. If you want the velocity vector at a particular point, you need to plug in the value of t. But we can look at the unit tangent in general. The unit tangent vector, and that has a special name. Well, the name is unit tangent vector, but it has a special notation. They call it capital T for the unit tangent vector. And one of our main topics in the next section is going to be talking about a collection of 2 or 3 vectors, a collection of 3 vectors that's going to be our local frame as we move along in space. So we have the unit tangent vector t. I have the derivative as a tangent vector. Do you remember how to make it into a unit tangent vector? Do you remember how to make a vector into a unit vector? Divide by the magnitude, right. So all you do for the unit tangent, and this is really just a formula, is you take your vector that you're looking at, our tangent vector, and then you're going to make it into a unit tangent vector by dividing by the magnitude. It turns out that helici, whatever the plural is for helix, these springs have a nice property in that the magnitude of the derivative of that is, well, let's figure it out. Let's try to find the magnitude. Let's find a unit tangent vector for this particular example, a helix. So I found my r prime of t. Let's take the magnitude of that. The magnitude of that is the square root of the first component quantity squared. So that would be 4 sine 4t squared plus the second component squared plus the third component squared, all added together. And what happens when you do that is you can kind of group things, foil, I guess there's no foiling here. You just take this 4 times 4, 16. You got 16 times sine 4t quantity squared and 16 times cosine 4t quantity squared. And you have the sine and the cosine together with a factor of 16. So if you imagine, can we do this in our head or should I write it down? It'll just be 16, right? And then you have one more, so it'll be 17. So this whole thing is just square root of 17. And if you want, you got 16 sine squared 4t plus 16 cosine squared 4t. That becomes 16 times sine squared plus cosine squared, which we know is equal to 1. And then plus 1 is 17. So again, the helix has this special property where the magnitude of the derivative is constant. That means as you're going around the helix, the speed, it's essentially the speed of this doesn't change. So that might have consequences later on that's important for us to take advantage of when we're studying other things. But to finish this, we really need to put this as a denominator of our actual r prime. So your t of t, the unit tangent vector, is going to be given by, well, we can just write this as a factor, a constant multiplied times a vector. So 1 over 17 times this whole big mess that we've had before. You can put it together if you need to. You can leave it like that. All right? So again, if your function is not necessarily a helix, the graph is not a helix, then there's a good chance that your length of the vector velocity function is not going to be constant. So you'll have a t in here, and then you can just treat that as a scalar function on the outside of the vector function, and then it'll work out the same. You can choose to leave it out here, or you can distribute it inside if you need to. All right, so we found the velocity vector, we found the unit tangent vector, and then now let's do an example where we're finding the tangent line to a space curve. And we kind of started to do this last time, but we didn't quite finish it. So let me do this by doing something a little simpler. Should we keep going here, or should I do the next page? You guys look at the notes, does it matter? If I extend this down, the font gets smaller and it becomes portrait instead of landscape. Next page. All right, so we're going to use the same function. So let me get the same function. Oops. And we actually need the derivative as well. We don't need the unit tangent, but we just need the tangent, the regular tangent vector. That'll help us. All right, so next page we have kind of like a point and a slope. We have the point and the direction. So let's find a value, a t value, where we want to find this tangent line. So in this page, we're looking for a tangent line. At t equals to, I don't know, we could put like pi over, I think we had pi over 8 at one time. So let's find a tangent line at pi over 8. So this is a line, bottom line is that this is a line, and we need two things for a line. We need a point and a direction. Well, if you just put the value of t into the original function, you get the point. So you got r evaluated at pi over 8. And then you get the direction by putting pi over 8 into the derivative. And so here are the two things that you need. And then we can just plug those in and then get our values. So what's r of pi over 8? You got cosine of 4 times pi over 8. That becomes pi over 2. Pi over 8. Sine of pi over 2. Pi over 2? I wanted pi over 4. Oh well. So cosine of pi over 2 is 0, pi over 8, and 1. So 0, pi over 8, and 1. And for the derivative, we put pi over 8 in for t. We got negative 4 sine pi over 2, 1, positive 4 cosine pi over 2, which is negative 4, 1, and 0. Okay? So now we have a point and a direction. After that, it becomes easy. Our line, let's call it L of t, is a vector. You can literally just put in the point and the direction, 0, pi over 8, comma 1, plus t times a new t. That's different from this t. So some people call this s, or some people call it t1 or something else, but let's just keep it as t. Negative 4, 1, and 0. So you can write it like that, or you can write it as a component-wise function. You got 0 minus 4t, pi over 8 plus 1t, 1 plus 0t. So you got your x, your y, and your z components. They're all linear functions. They draw a line, and we're all good. So you can say in general, your equation of a line, L of t, is going to be the point, and usually you are able to get the point by putting your some t value into the what? General. Plus t times r prime t naught. All right, any questions? Before we do any integrating, let's do another quick example of finding the unit tangent vector where we're not talking about a helix. And in fact, I think the example that I'm looking at takes a look at just a two-dimensional vector. You can think about a two-dimensional vector as a vector in 3 dimensions, except it's on the xy plane. There's no z component, or z component is equal to 0. So let's approach it that way, and then it's kind of like looking at a space curve. So let's do another example. And I'll write it a little bit differently because I want you to kind of get flexible with the notation. So the i's and j's, remember, just puts them into proper components. And if you had a k, that would be like in a third component. So you can easily rewrite this as parentheses t cubed comma t to the 6 close parentheses as a two-dimensional vector valued function. Or you can throw in a 0 for the z component and then pretend that this is a three-dimensional vector valued function. But we'll just look at it as a 2D kind of function. All right, let's find a unit tangent. So to find a unit tangent, what we need to do is we need to find the the tangent vector, the velocity vector, by taking the derivative. So step 1, find just the regular derivative. And now I'm going to switch notations on you and say this is 3t squared comma 6t to the 5th. Did I do my derivatives right? Yeah, looks good. So this is our first step. Next is to try to find the magnitude of that. So to find the magnitude, we just take that very same thing and do the square root of 3t squared quantity squared plus 6t to the 5th squared. Let's see if we can simplify this. This is 9t to the 4th plus 36t to the 10th. I don't know if it's worth doing anything else here. We can manipulate it a little bit, but take a t to the 4th maybe. What? A 9 would come out to. So 9t to the 4th, we got 1 plus 4 t to the 6th. So we got a 3t squared sitting outside, if that's of any use or whatever. So if you just take the ratio of this, or I don't know if ratio would make sense since the first number is a vector and the second number is a scalar, not number, but the first thing's a vector, the second's a scalar. Your t of t is equal to, I'll write it a couple of different ways, 3t squared comma 6t to the fifth divided by 3t squared square root of 1 plus 4t to the sixth. That would be seems like the obvious way of writing it. But you can perform the scalar multiplication if you want by multiplying this through. And then if you multiply this through, since this is in the denominator, that would cancel that first one. So that would just leave us with 1 over the square root of 1 plus 4t to the sixth, comma. And then we can simplify a little bit. This would be 2t to the third. Or you can also factor in the denominator. I'm just writing different forms. These are all the exact same answer, although this last one is easier to write. So this is our unit tangent function, unit tangent vector. All right. So what this is saying is that as you move along the curve, your tangent vector's length will be changing. The length of your tangent vector is changing. By the way, I should have said something else about the length of the tangent vector. Turns out that the length of the tangent vector is also, well, I guess this is in the next section, it also gives you the speed. Since we're not really talking about particles in space yet, we're talking about the geometry of the space curve. But this would go under the next section when they start talking about motions in space. Note that the magnitude is the speed. And if you looked at your accelerations and velocity and back in Calc 1 and Calc 2, the velocity is only either positive or negative. It's a scalar function. It's a scalar, which means it's a number. And the only difference is that if it's going up, it's positive. If it's going down, it's negative. That's how we used to measure velocity functions. But now the velocity here for something that's flying through or something that's on a particular path in space, the velocity here is given by a vector. So vector, remember, has direction and magnitude. So the direction of the vector tells you which way you're going. And the magnitude, significantly enough, is the speed, how fast you're going. So in this case, since our magnitude is a function of t, what that means is that our magnitude is going to be different for each value of t, which means our speed is changing as we go along this curve. So our first example was a helix. That's usually our first example for a lot of things because it's a nice, easy function, and one of its special properties is that the speed doesn't change. It goes around in a circular fashion. I mean, it moves away from the circle. It goes like on a spring, but it still goes at a constant speed all the way through. All right, next thing I want to do is integrate. Let's do some integrals. So let's take the same example here and integrate this. So here we're talking about integrating vector-valued functions. And we would normally like to think about integrating vector-valued functions as doing something like this. But this, we don't really know how to integrate a vector, and you'll see that it really comes out to be something really simple. But the idea is that we want to be able to define an integral of a vector-valued function. And so the way we're going to define it is to take a look at R as x, y, and z. They're all functions of t. And really what we have here is the integral of the first function with respect to t, the integral of the second function with respect to t, and the integral of the third function with respect to t. So there's no surprise there. It's just like how we did the derivative. We took the derivative component-wise. Similarly, we're going to take the integral component-wise as well. Now, what kind of integral is this? I don't know if that was a fair question. What kind of integral is this? No. Standard. What? No. Indefinite. I think you might have meant to say indefinite. This is an indefinite integral. There's no limits. All right, so there's no limits. If there's no limits, it's an indefinite integral. If it's an indefinite integral, what do you need to remember? Otherwise, you lose a point. Plus c. Okay. So each of these components will have a plus c, right? And so when each of those components has a plus c, you, in general, have a vector of constants. All right? So think about integrating this as, I'm going to use capital X as a notation. That, you know, the antiderivative of a little f is capital F. So I'll use capital letters x of t plus c1 y of t. Y, capital Y is the antiderivative of little y, plus another constant c2, and then z of t, the antiderivative of little z, plus c3. And so, let me just make a note here just so we're clear. X, y, and z, those are my capital X, Y's, and Z's, are the antiderivatives of x, y, and z. A little side note. So this is my result, and what happens here is that sometimes we might express our results with the antiderivative. I mean, we did it piecewise, so it makes sense to put a plus c in each of those. But we can also take a look at it maybe I'll call it c, a the vector c, where c, the vector c, is equal to c1, c2, c3. So what I'm saying here is that that constant that comes out in each of those components can be written separately as a vector, and that might come in handy later on when we're working on stuff if we want to kind of shorthand our way to things. Oh, there is an example I wanted to do. I'll do it in a minute. Anyways, just as an example of an antiderivative, let's take this problem that we were working on earlier. And let's find the integral of that. So the integral of r of t in this case. So this only has two components. I won't worry about the z component. So I'll just take the antiderivative of each of them term by term. I'm going to go back to my parentheses notation. T cubed, the antiderivative, I think is t to the fourth over 4. And then t to the sixth is t to the seventh over 7. And I can decide to put the plus c within the parentheses here, or I can just say plus c1, c2, whatever's convenient. I guess I'll write it both ways. T to the fourth over 4 plus c1, t to the seventh over 7 plus c2. So the applications of this would become a little bit clearer when we start looking at motions in space, and we'll do that again in next section. Okay, I think there's a lot of other formulas that might be important to look at that I'm not including in this lecture right now, but we'll come back to that next time. Any questions? There's this special function here. For some reason they use w instead of t. I was trying to do research on this, but I didn't really have too much time. But here's a function. R of w is equal to w in the I direction minus ln of cosine of w in the j direction. Between negative pi over 2 to pi over 2, because I guess at pi over 2, positive or negative pi over 2, the cosine is 0, and the ln doesn't like the cosine, or ln doesn't like zeros. So this, by the way, is it looks like a fairly simple graph. It's not quite a parabola. It just drops down. But it's called the Grim Reaper for some reason. Interesting fact. Grim Reaper. Let's find the derivative and then the unit tangent vector. And then let's try to take a look at the graph of these things. So let's find r prime of w. What's r prime of w? I. And whatever this is, right? Remember how to take the derivative of an ln of something? 1 over cosine omega. Since x is not the simple x by itself, you have to take the derivative of the inside via the chain rule. Derivative of sine, negative sine, or derivative of cosine, negative sine. Oh, there's a negative in front of this that I forgot to put on, so let's put the negative there. So this basically is just 1, and positive sine over cosine is what? Tangent omega, or tangent of w. Okay. Let's find a unit tangent vector. Let's find the magnitude of this. So the magnitude is the square root of 1 plus tangent squared w. Is that something? That's secant squared, right? So it's under square root, so it just becomes secant of w. That's interesting. So that means your unit tangent vector is 1 over secant of w times 1 comma tangent of w. Can we simplify this? What's 1 over secant? Cosine, right? And cosine times tangent? Sine. Oh, that's kind of cool. So that's your unit tangent vector. So they want us to find specific values for w. Let's find a couple of them. Let's find out when w is equal to, let's put negative pi over 4, 0, and let's do pi over 3. So, you know what tangent of negative pi over 4 is?
1.
I don't know, 1 or negative 1. But that was... So, 1, comma, negative 1? R prime is 0. Tangent of 0 is what? I'm putting these w values into the into this function. Tangent of 0 is 0, and r prime of pi over 3. What's the tangent of pi over 3? Root 3? It's either 1 over root 3 or root 3. Root 3? Okay. All right. Let's put these values in compare. Well, if you look at them, they're going in whatever direction they're going, but they're not in a specific what do you call it? Whatever. So let's try putting the same values in for your tangent, unit tangent. So negative pi over 4 into the cosine, I think it's root 2 over 2. And I think the sine's negative, but the cosine's positive. So cosine's positive, so that becomes positive. This goes negative. So it's really just the magnitude. It's just the unit vector going in the same direction, right? And if we put 0 in, we're going to get cosine of 0 is 1, sine of 0 is 0. And that's the same thing as this, because this is already a unit vector. And then if you try putting pi over 3, cosine of pi over 3, 1/2. Is it? And then sine is root 3 over 2. Which should be the same as this, except it has unit length. So that makes sense. So let's take a quick graph of this, just so we can get a visual of what's going on. Oh. Whoops. So let's graph our Grim Reaper. Let's have to use t because this graphing program only understands t. Negative ln of cosine of t, and we're going to go from negative pi over 2. We don't want to go all the way to negative pi over 2. Because it's kind of undefined. So it looks like this. This is how the graph looks like. Our first vector is negative 1, 1, and this is at pi over 4. So for me to graph a vector here, I need to go from tail to head. And if I just go from tail to head, I need to specify where I want this graph to be. And so I can start with 0, 0. And then add on that point. 1, comma, negative 1. But it's going to give me this vector down here, which is not useful, right? So I want to move that. Instead of starting at 0, 0, I want to move it so that it's somewhere else It's where it belongs. So how do I know which point to put it in? Any ideas? Do you understand what I'm asking? I want to know where to put this vector, the tail of this vector, so that it makes sense to this graph as a tangent vector. Yeah, how do I find the point? How do I find the position? Just plug it into the original equation. So this is the original equation. And I'm going to do something just using functions here. So instead of t, I put in, what did I put in? Pi over 4? Negative pi over 4. This is where this kind of gets a little messy, but so if I put that as my starting point, then I will be tangent now. Can you guys see that? It's really light. I don't know if that's any helpful, but now it's at least it looks like it's tangent. So instead of looking at that, what we can do is we can take a look at root 2 over 2. Again, hard to see, but it's they're the same vector, except one of them is a little bit shorter than the other one, or one of them is of unit length. So this thing has a few other questions that I kind of want to follow along with, but I think we're kind of running out of time. We need to move on. But there's some interesting questions about finding perpendicular vectors to this. This turns out to be an interesting function in a sense that how did they put it? This curve is called the Grim Reaper because as t increases, it appears to eat itself up. I don't know what that means. All right. Well, we'll see. Okay, let's get started with another concept. So we know how to take derivatives and integrals, and we got some geometry out of this, and we got some calculus out of this. Now let's take a look at the idea of finding an arc length. So this moves us to the next section, arc length. And what we're going to do is we're going to refer back. Well, I guess we'll take a look at this section is actually called arc length and curvature. And so when we take a look at curvature, we'll refer back to the unit tangent vector, because that tells us a little something. If we fix the speed of your path, then we're really just focused on how things are curving. And so we're going to use the unit tangent vector to measure our curvature. But we're going to first talk about arc length. So let's talk about arc length. I think we did arc length for parameterized functions already. You remember? In 2D. we had x and y to define our parameterized function. We had two functions, and then we found the arc length. I think we call it S is equal to the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. So it turns out that in 3D, we really do the same sort of extension. Remember that this x prime and y prime comes from the distance formula, and how really what's happening here is that you're taking this and you're breaking this up into little pieces, and then for each of these you find the length, and then the length would just be a change in x and the change in y, delta x, delta y. And then that's, I think it was in one of the lectures that we did, and when we talked about parameterized equation, we found a formula for the arc length that way. So if you imagine going to 3D with the same sort of picture, now instead of just having delta x, delta y, you'll have delta x, delta y, delta z, a change in x, y, and z. So if we follow through the same procedure, the arc length is going to be pretty much the same way. Can be written as a to b square root of x squared, or x prime, sorry, y prime squared, and z prime squared. But if we stop and think about this for a little bit, does this thing inside of the integral look familiar? I guess I could ask the same question up here. Let me rewrite this a little bit better, where r of t is equal to x of t, y of t, z of t. Now, if we look at that thing inside of the parentheses, does that look familiar? It's what? Yeah, it does. It does. Oh, it does. What does it look like? Distance? It's what? Magnitude of the derivative. Yeah, kind of like the distance. Essentially, it's the length of your velocity vector. How do we write that shorthand? Magnitude of, not just t. So this is the magnitude of the velocity vector, which means we can essentially rewrite this. This is close. Magnitude of the velocity vector. Yeah. That makes a nice short notation for it. Not quite, because we need to take the derivative of that, and then it has to go under the square root, and so it goes through a little bit more process. You can't just, like this one, you can't just undo the square root because you're adding things in the middle. All right, so if that's the case, then we sure should be able to find the arc length of things pretty easily, right? Yeah, right. And what's the easiest example to do when you're looking for curves in three-dimensional space? A helix. Let's take a look at a helix and find the arc length of the helix. Example. Let's say r of t is equal to cosine t, sine t, and 1. And let's find the arc length from, let's just go from 0 to 2 pi. So if we're just going to go from 0 to 2 pi and find this length, all we really need to do is find the magnitude of this, right? And then we're going to integrate the magnitude from 0 to 2 pi. So the magnitude, well, I guess first we need the derivative. Can I just do it in one step? I forgot to. So the derivative of cosine is negative sine, but you're going to square it anyways. The derivative of sine is cosine, and then you'll square that. The derivative of 1 is 0. And so this is sine squared plus cosine squared, which is just 1, and the square root of 1 is just 1. See? Nice function. Helix. So that's it. We're just going to integrate. So the arc length is going to be the integral from 0 to 2 pi of 1 dt. That's just t from 0 to 2 pi. So that's just 2 pi. So it turns out that the length of a helix, going from 0 to 2 pi, is really the circumference of the circle. So imagine just taking a circle, a ring, and then like your keychain ring, and just try to stretch it out like that. It's still the same length, you just kind of stretched it and moved it away from each other. Pretty interesting, huh? Of course, it's really hard to put the keys in. It's hard to stretch it apart. So imagine your circle that just got moved up. It's the same length. Something a little bit more interesting is that other function that we had. Let's do just one more quick example. It's not going to be so simple. R of t is equal to, what was it? T cubed and t to the 6. But there was a constant in front. Do I still have it? No. What is it? Oh, just t cubed? Okay. Yeah, so the derivatives will have constants. So we already did the work, so can you just remind me what the magnitude of the derivative is? Some 1 over 3t. No, that was the... Oh, we should have done that one. Yeah. Why is it what? Oh, I don't know. Yeah. Okay. So in non-helix examples, you're going to be faced with integrals that generally would look a lot more complicated. And this one, you could probably do some fancy trig substitution to find the arc length and stuff like that. But in general, the arc length formula, because of the square root of each of them being squared, it's going to end up being a lot messier. I didn't put limits here, so let's go from 0 to 1. So, for example, doing an integral like this is not easy. You can't just use a U substitution, which is the easiest kind of tool, and you have a square root. So there's a good chance that if you were to do this by hand, you would need to do trig substitution. So in general, in the test situation, test quiz situation, I would probably just have you set up the integral to find the arc length without having you actually find the arc length. And in homework situations, you're more than welcome to punch it into Wolfram Alpha and get the results and answer it that way. Okay? All right, so next time we're going to talk about curvature. We're going to take advantage of our knowledge of the unit tangent vector and then find the curvature using that, and then introduce a couple of other vectors to help us define a local frame as we move along space. Okay.